Today's notes are our first formal introduction to quadratic functions. So a quadratic is a type of function. We've done linear functions this year, and we've done exponential functions. And the final type that we learn about in Algebra 1 are quadratic functions. In Algebra 2, you'll learn about lots of other kinds of functions as well, but this is our main focus for the rest of the year. So a quadratic function, or a quadratic, is a polynomial. So it's a quadratic is a polynomial, which is why we've been working with them, where the highest degree of any variable is 2. So you may recall that we started the year with linear equations, which were degree 1, something like x plus 3 is a line. Quadratics have an x squared term. So they have x squared plus 2x minus 4 or something like that. So that should look familiar from what we've been working with in polynomials recently. A parabola is what we call the shape of a graph for a quadratic. So a parabola is like a U-shaped graph created by a quadratic function. So we know lines are straight, like that, and quadratics have a curve. So they have a feature called a vertex. Vertex is this point right here where the graph turns around. And the root word vert in vertex literally means to turn. So invert or convert or even vertical all have that same kind of root word that has to do with turning something. So this is a literal turning point within the graph. A graph, different functions can have multiple vertices, but a quadratic only has a single one. Higher order or higher degree polynomials may have more vertices and not just a single one. So the vertex is the minimum, which is the lowest point on the graph. So you can see this U-shaped graph down here. It has a lowest point at the origin. But we can also cause vertical reflections, just like we could with lines. We can vertically reflect any kind of function or graph. So if we reflect it, then that turning point becomes a maximum instead. So maximum is the biggest, so this here would be a max, and this here would be a min. So we have parabolas have a feature in that they have left to right symmetry. So they have a vertical line of symmetry right down the middle. And a formal mathematical word for line of symmetry is axis of symmetry. So you know that an axis is just a fancy name for a line, like we have the x-axis is this line right here, and the y-axis is that line right there. So it's just a fancy word for line of symmetry, meaning that if we split the parabola vertically, we end up with a mirror image on the left and the right side. So it always passes through the vertex. The vertex is the spot where the graph turns around, therefore it is the center of everything symmetrical. So it's kind of like this unique point in the middle, and everything aside from that is a mirror image to the left and the right. This parent function, you remember we had a parent function for lines. It was y equals x, the most simple line you can make. Similarly, our parent function for quadratics is just y equals x squared. No x term, no constant term, so we don't have any of these things in there. It's just y equals x squared, the simplest thing it can be. We'll talk as we go forward about standard forms of quadratic equations. So just like we had forms of linear equations like y equals mx plus b, our primary form of quadratics is called standard form. It's a little different than linear standard form, and it looks like ax squared plus bx plus c. So in this case, for our parent function, a is equal to 1. We just have 1x squared, and we zero out these other ones. There's no b and no c. Kind of like in our parent function, y equals x, this b, the y-intercept, was 0, and the slope was 1. Same exact kind of thing. So standard form for quadratics is a lot like slope-intercept form, which was the first linear form we learned about. If we looked for points on this graph, the easiest one to start with is the vertex itself. It's at 0, 0, the origin. And then if we go 1 unit to the right, we go up 1 unit squared. So we end up going up 1. So from here to here is plus 1 in x and plus 1 squared in y. So plus 1 and plus 1 squared. From 0 to 2, so we can't go from 1 to 2 like we can on a line. We can't go from point to point. We have to go back to the vertex. So if we go 2 away from the vertex, then here we go 2 squared away from the vertex. So you can kind of see the pattern. Y is just doing the square of what x does. So if we go 3 units from the vertex, we go up 9, 4 units, 16, 5 units, 25. And then, since we know there is a line of symmetry right here through the vertex, everything going left does the same thing. So this is 1, 4, 9, 16, and 25 going back the other way. One interesting thing here, so if we look at the differences between each line, so our difference here is 9, 7, 5, 3, and 1. So kind of obvious that it's not linear, because in a linear relationship, this difference would be the same at every step. But you probably saw that there was a pattern here. If we look at the difference of the differences, so we call this the second difference, we have 2, and 2, and 2, and 2. So this is not really an Algebra 1 topic. Usually I don't think it's more Algebra 2, talking about a second difference, but there is kind of this idea that something is constant between terms. But we can't get that from just 2 terms. We can't get it from just looking at 9 and 7. We actually need, or 3 terms. We need 4 terms to get 2 second differences. So that won't be that useful to us, but it is an interesting pattern that you might have picked up on. All right, the domain and range is where we close out this part of the notes. So our domain for pretty much, well, for all polynomial functions, so for lines, parabolas, and anything bigger polynomials, our domain is always all real numbers. We can write that this way, or in inequality notation, negative infinity is less than x is less than infinity. Remember, we can never equal infinity because it's beyond all numbers. And then our range is not all real numbers. So remember, we did linear. Lines have a range of all real numbers. And we did exponential. Those had a different kind of range because they had an asymptote in their graph. So they went something like this and approached a value, and r was y is greater than the asymptote value, which normally was 0, unless we change that somehow. So this one, a quadratic, is similar to exponential, but there's one slight difference. So it actually does reach the vertex where it turns around. So the range here is y is greater than or equal to the maximum or the minimum value. It could also be y is less than or equal to if it was a maximum. So our range here, y, can be anything greater than or equal to 0. In inequality notation, or full inequality notation, our minimum value is 0. That's less than or equal to y, and that's less than infinity. If we inverted the graph like we did here and reflected it vertically, then we would end up with a negative infinity, less than y, less than or equal to whatever the maximum is. And I think we'll have a chance to see that a little further down. So this page shows us a diagram with all the vocabulary for a parabola. This is going to be a really good resource to have when you're studying for quizzes and tests to remind you what all the important things are. So we're going to start with the most important point on the parabola. This red dot up here is called the vertex, as we said on the first page. We're going to put a few important pieces of information about the vertex in this box. Some of them may not make complete sense yet, but they will over the coming days as we learn more about this. So if something doesn't make sense yet, still put it in your notes because you're going to refer back to this when you're studying. So first of all, we're going to put the vertex has the coordinates h, k. You may remember from linear transformations and function transformations that h represents a horizontal shift or a horizontal translation, and k represented a vertical shift or translation. And that's the exact same thing here. So looking at this, h and k is basically telling us how has the graph translated relative to the parent function, because we saw up here that our vertex originally started at 0, 0. So wherever it is now, that's how far the whole graph has moved to the right and up. In this case. So our coordinates here are 1, 9. So we have a horizontal shift of 1 and a vertical shift of 9. The other things we probably want to put for vertex is that it can be a max or a min. It is a maximum when the coefficient of x squared, remember we call this number a, is a number less than 0. So a is less than 0, or you might put a is negative. So this one, where it's a reflection, you see that we have a -1 coefficient for x squared. So since that number is less than 1, that means the graph is upside down and we have a maximum value rather than a minimum. In our parent function, we saw that when a was positive, so for example here a was positive 1, we had a minimum value. So that occurs when a is greater than 0, or you could say when a is positive. So those are some important features of our vertex, and we'll talk a lot more about vertex and vertices as we move forward. This point here, right next to the red one, this green dot on the y-axis, you might assume or imagine is the y-intercept. So just like the y-intercept of every other function we've dealt with, we think of that as an initial value. And in this case, it has the coordinates 0, c. Remember that c is our constant. Not because it's a c, just because we call the coefficients here a, b, and c. So here we have a is -1, b is 2, and c is 8. So our y-intercept, and you can see that pretty quickly if you plug in 0 for all of the x's, all you're left with is that 8. So our y-intercept in this example is 0, 8. And it's just the same as any y-intercept of any graph is. Next, we're going to drop down to these two dots on the x-axis, the purple and green ones here. These are the x-intercepts. And we've mentioned earlier in the year, but there are several different vocabulary words that we use for x-intercepts, and you need to recognize all of them. So x-intercepts is maybe the least used one. The most used one is we call them zeros of the function. So a zero of a function means f of something is going to output 0. So that's the same thing as an x-intercept. It's saying what value of x is going to create a y value of 0. Another term we use is roots. And another one is solutions. So thinking about linear equations, if you had like x minus 3 equals 4, or I guess equals 0. Let's do equals 0. X minus 3 equals 0. The solution to that would be x equals 3. So as we get into not just graphs, but solving quadratic equations, it will be important that the x-intercepts represent solutions to the problem. These x-intercepts are sometimes represented with the letters P and Q. So we can write a lot of quadratics, not all of them, is a product of two binomials, and we saw that when we multiplied polynomials. Remember, we had a area model where we multiplied like x plus 2 times x minus 7, and we ended up with a quadratic trinomial. So this gave us x squared minus 5x minus 14, and that quadratic comes from these two binomials here. So the zeros can be represented, or the solutions can be represented in terms of two binomial factors of the quadratic, and that's a topic we'll get into more later. But for our notes here, we're just going to note that these can be called, these are x-intercepts, not y-intercepts. One of them is at p comma 0, and the other is at q comma 0. And we write, so we talked about standard form. We have a different form of quadratics called factored form. And factored form is simply a product of two binomials. So factored form is written as a, the same a, which represents a vertical stretch here, times x minus p times x minus q. So p and q represent our x-intercepts, or our solutions to the equation. And I think that's good for x-intercepts. Yeah. Well, yeah, let's leave it there. And we'll go down to this bottom box, which is, as we wrote in our first page, the axis of symmetry. It's the line right through the middle of the parabola that splits it symmetrically. We usually abbreviate it as AOS. And a couple of important things to note for it is how to find it if you're not given a graph. So if we're given the factors, so we have factored form, then we would take p plus q and divide by 2. So what that means is, and we call the axis of symmetry h. That's the same h that we had in the vertex, our horizontal shift. Because if you think about the original parent function, what we've done is we've moved it to the right 1 unit. So our horizontal shift is 1, and now the axis of symmetry is here. The axis of symmetry, since it's symmetric, is always exactly halfway between the two zeros. So however far away the zeros are, they're the same distance. So if I average them, I take the average of their two locations, I'll find the point exactly in the middle. So for example here, this one is at 4, 0, and this one is at -2, 0. If I average those two numbers, I would do 4 plus -2 divided by 2, which is 2 over 2, so my axis of symmetry is at 1. We always write the axis of symmetry as an equation of a line. So here we would write x equals 1 being the axis of symmetry. It's never enough just to put a number. We need an equation because it's a whole line, not just a single value. And the last thing we're going to put in this box is a way to find h from standard form. So this is on the star chart. It's the very bottom row on the algebra star chart. It says that the axis of symmetry is at -b divided by 2a. So that b and a are the coefficients in standard form for the x term and the x squared term. So as an example here, b is 2, so I would do -b over 2 times a is -1. So I get -2 over -2 equals 1. And again, that tells me my axis of symmetry is at x equals 1. That covers that box. And then our last box is some other points on the graph. So points on the graph. And these points have a common structure, kind of like a line does, but it's a little more complicated. So in a linear function, I'm just going to sketch one right here, we could find a slope by taking a rise over a run. So we had rise and run, and we found the slope as the rise over the run. But here, x and y aren't related linearly. For every rise, the run kind of happens twice because of the squaring. So instead of rise over run, we can find this A value, basically the vertical stretch, by doing the rise over the run squared. So that would let us find the A value from a graph and know what our vertical stretch factor is. So I didn't put over here, but A, as it is for all polynomials, the leading coefficient. So this was our leading coefficient, but it also is the same A that we had in transformations, and it represents a vertical stretch. And it tells us how wide or how narrow the parabola is. So we can find that A value from a graph by looking at the rise over the run squared, but only from the vertex. So we have a table of values over here that come from this graph. They're all transformations of the original table here. So our table for the parent function has had a few changes applied to it. So in this case, it had a horizontal translation to the right, a vertical translation up, a reflection, and then it wasn't stretched at all because we still have a 1 for this A value. So applying those three changes changed all of these point values to their new locations. And then finally, our domain and range. So this one has a maximum value. Our domain is still all real numbers, and unless there's a limitation of an applications or word problem, or it just states a domain limitation, that's always the domain. And we can write all real numbers or negative infinity less than x less than infinity. Our range this time, though, we have a highest value, but no lowest value. So this graph is drawn on a computer. It doesn't show the arrows, but the line running off the edge of the graph tells us that it continues. So our range starts at negative infinity. That's less than y, and then y is less than or equal to our maximum value, which is 9. And there we go. So that is our domain and range. We can also write the y more simply as y is less than or equal to 9, and that shows that it has no lower limit, but this is the more complete way to write it. All right, so that's notes. Let's look at a few examples that are like your homework problems so that we can see how we answer those. Number 1, we are identifying the axis of symmetry. So we look for the vertex and we look at where the x coordinate is. So it's over 2 units to the right. So we write the AOS as x equals 2. Remember that this needs to be an equation of a line, not just a value. Now we're going to take that value, x equals 2, and we're going to reuse it because that's always the x coordinate of our vertex. So those two always go together. Then we're going to look for our y value of our vertex. So that's down at negative 1, negative 2, negative 3. So we're going to put negative 3 as our y value. And our y value of our vertex is always going to be our min or max value. So min or max value is not an equation. It is just a number. So this is a single number, not an equation. It's different than the axis of symmetry, which is a line and needs a whole equation. Here we're going to circle minimum to say that this is a lowest value, and we know that because the arrows point up, and this is the lowest point on the graph. A lot of times these also ask opening directions, so this one opens up. And that just goes along with the idea that it's a minimum. These two go together. I guess I should pick a different color for those. So opens up is the same answer as max or min. Min always opens up, max always opens down. So you notice there's a lot of overlap. So if you understand what these features are, you kind of get to repeat them for free, and you just need one answer that fills in several different things. In fact, we weren't done with the minimum or the k value in the vertex. We also know that that determines our range. So our range is -3 is less than or equal to y is less than infinity. So we have that same value, -3, shows up in 3 different spots. It's the y value of the vertex, it's the min or max, and it limits our range because it's where the graph stops and turns around. Our y-intercept, we just look at the y-axis, and it's at 0, 1. We should write that as an ordered pair to differentiate it from the x-intercepts, or remember, we often call these zeros or roots or solutions. The x-intercepts here are not at even values. We'll talk a little bit later about how to find those exact values, but for right now, we're just going to estimate and say that they're at about 1/4, 0, and at about 3 3 3/4, so about 15/4, 0. And I promise we will find out exactly how to know what those numbers are a little bit later. Our domain, as pretty much always, is going to be all real numbers. Okay, I had to pause and make a cut there real quick, so we're going to start with number 2. Hopefully I just finished number 1. So here we have shifted the graph 3 units left from where it started at the y-axis. So our axis of symmetry is x equals -3. Our vertex, then we know it has a -3x coordinate. The y coordinate is 2 from the graph. This graph opens down. Opening down always corresponds with a maximum value because there's a highest point, and that maximum value has to be the same as the y coordinate of the vertex, which is 2. Our y-intercept here is at -1, 2, 3, 4, 5, 6, -7, so we write that as 0, -7. Our x-intercepts, again, are in between numbers. It looks like they are approximately -1.5, 0, and -4.5, 0. Our domain is all real numbers, and our range is going to be -infinity, because we're heading down forever, is less than y is less than or equal to 2, which, remember, again, is a repeat of our maximum value and our y value of our vertex. Then our final example, our axis of symmetry has not moved. It is still on the y-axis, and the y-axis has the equation x equals 0. So every point on the y-axis has an x value of 0. Our vertex then is 0, and we look at the graph, our y value is 2. That opens up and has a minimum value of 2, that same number. I have no idea what that is. Let's try and make a normal 2. There we go. Our y-intercept is our vertex in this case. So since we didn't shift left or right at all, then the vertex is on the y-axis, and our y-intercept is 0, 2. Our x-intercepts, this is a little different because we never reach the x-axis. The graph turns around before reaching the x-axis. So we're going to say that there are no x-intercepts. And a better way to answer that, and what we'll put as an answer on problems when we're solving quadratics, is to say that there are no real roots. So in Algebra 2, you'll learn about complex numbers and learn that there is a way to solve this and find 2 solutions to this, just like to all the other problems, but they're not real solutions. They're called complex numbers and involve a thing called an imaginary number. So that'll be Algebra 2 stuff. Our domain is still all real numbers, and our range is 2, that same number we had in our minimum value, is less than or equal to y is less than infinity. So there's some examples. Hopefully that helps you to identify all those key features in your homework.